So welcome to session 5 on GPUs, and the first speaker will be Josh Milthorpe from Oak Ridge National Laboratory, and the title of his talk is Accelerating Data Analytics with Arkouda on GPUs. Josh, go ahead and take it away.
Thanks, Arumi. I'm Josh Milthorpe. I'm speaking today from the traditional lands of the Cherokee people in Oak Ridge, Tennessee. I'm in Jeffrey Vedder's group at Oak Ridge National Lab. And I'll just make sure my slides will carry through. Okay, good. So as you've heard, Arkouda promises high-performance computing enabled exploratory data analytics. And really what we're talking about is computing on large data. And when we're talking about large data, we're really talking about needing very large memory bandwidth. When we look at the two most recent supercomputers that we have here at Oak Ridge, Summit and Frontier, one thing you notice is that while the bandwidth available to DRAM, the host memory, has actually reduced somewhat in the move to the latest generation with Frontier, the bandwidth available for GPU memory has increased massively. And so you can imagine if you're only using host memory, if you're only able to use your CPUs, you're really only able to use 1/60th of the total memory bandwidth available to you on the Frontier system. So avoiding GPUs is not an option for Arkouda and large data. We really want to be able to use all of the system available. So what are the challenges for using GPUs in Arkouda? A big one is always going to be algorithmic portability. It's not necessarily the case that an algorithm that works well on a CPU architecture is going to be performance portable to GPUs. In addition to that, there's also the problem of memory management. So you've got large data. You need to think carefully about the best place for those data to reside at different points in the workflow, and how best and when to transfer between different devices and different memory spaces. And of course, you have a programmability challenge. If you're now developing additional code for different GPU devices, how do you manage that complexity? And so we'll look at ways to address all of these challenges. Okay, so really briefly, the Arkouda architecture, as you might well know now, is based around a Python client. So the data scientists write Python as they used to, as they love. But behind the scenes, we're communicating with messages over ZMQ to a Chapel server, which represents Arkouda arrays as Chapel distributed arrays, and implements all of the core operations on our arrays as distributed algorithms over our cluster. And so we're not looking to change the Python client in any way. What we're looking to do here is add some GPU-specific code to the implementations of Arkouda operations so that we can map them down to run on the accelerated devices we've got available. So when we started this work, the obvious choice for writing GPU implementations for Arkouda was the Chapel GPU API. This is a Georgia Czech developed framework, and Akihiro is going to talk about it in the next presentation. This framework abstracts over the various GPU programming models that you have available, like CUDA, HIP, DBC++, and SQL. So it's really nice for multi-vendor development work. There are two main components to GPU API. There's the GPU iterator, which allows you to expose the parallelism in your application in a Chapel-like way through Chapel's data parallel loops so that you can launch them as kernels on your GPU device. And then there's the GPU API itself, which provides wrappers around the various device functions so that you can do things like device and memory management. That's at the low level, and then they also have a mid-level, which is called things like GPU array or GPU jagged array. This helps you to manage your memory allocation and transfer between different between host and device. You'll notice there's no high level in the GPU API. I think what that means is that they're assuming that eventually the high level will be taken over by Chapel GPU code generation. Okay, so how would we use the GPU API at the mid-level to implement a simple operation in Arkouda like a sum? So we're just doing a sum over a vector, and we're wanting to do this on GPU devices. So we might divide the vector into multiple chunks, one for each device. And we're going to perform, this is on a single Chapel locale, multiple GPU sublocales. We're going to perform a per device sum. And then we're going to sum all those partial sums together to get the host, on the host side, we're going to get a sum over the entire vector. Okay, so with the GPU API, it provides a few things to us. It provides the GPU array, which I said allows you to allocate memory and transfer to the device and from the device. It provides wrappers for synchronization on the GPU, and it provides a way to take a Chapel data parallel loop and launch it as a kernel on your GPU device. And this kernel launch is just really a C wrapper around your CUDA or your OpenCL code or whatever. Okay, so this is how we started using GPU API. But what we noticed is there's a really common pattern when we're implementing our CUDA operations, that we need to create these GPU arrays to represent the local device chunks of our CUDA arrays. We're copying data from the host to the device. We're launching the kernel. We may launch multiple kernels, and then we may copy some outputs back from the device to the host. So we want to represent this pattern so we're not writing a lot of boilerplate every time. We also, if possible, would like to leave data on the GPU rather than transferring backwards and forwards unnecessarily between operations. So what we created was a thing called a device cache. This is an addition to Arkouda's SIM entry class that represents Arkouda arrays. And what the device cache does is just allows us to hold on to those device chunks, the representation on the device, and as needed, transfer to or from the device and maintain the data cache on there for when we need it. Okay, so using the device cache, our code looks a little bit different. Before every operation, we just call this create device cache operation. That's idempotent. If we do it more than once, we don't create additional memory. It'll just remain there on the device. We call a toDevice function on our device cache. Again, that's idempotent. So if the device already contains our necessary data, we're not launching an unnecessary transfer. And then we can use the device cache, the local chunks, to perform our CUDA operation, in this case, a sum. Okay, so having looked at this slightly more efficient way of caching data on the GPU, we also wanted to consider the use of unified or shared virtual memory in Arkouda. So this is a common programming concept amongst all the different GPU vendor models. The idea of unified memory is that you have the host and the devices in your system sharing a single pointer to a unified memory space. But whenever we make an access to memory that is in a different physical memory space that's currently mapped to a different physical memory space, that's going to result in a page fault, and that page fault is going to transparently migrate the page of memory to where it's now being accessed. So this is really nice from a programmer point of view, and we wondered if we could use this to speed up GPU array implementations of CUDA operations. And I should say this is also the basis of Chapel GPU code generation. So what we did was create a new user-defined Chapel distribution called GPU Unified Dist. This is essentially the same as Chapel's block dist, but instead of allocating memory in the normal malloc way, it allocates its local chunks of memory using a GPU unified pointer. And we modified Arkouda's SimArrayDmap class so that if we're using GPU memory for an Arkouda array, that's going to be allocated in unified memory. And so this tiny little diagram on the side here is basically showing we can now create Chapel distributed arrays, domain mapped using our GPU unified dist. And what that means is the pointers to elements of our array are going to be in unified memory. So they may be physically stored on the host or the device, but our page migration engine is going to handle moving the data to where they need to be. Okay, so when we implement our Arkouda operations using our GPU unified dist, now all we need to do is operate on regular Arkouda SIM entries. These are Arkouda arrays, wherever the GPU flag is set to true for that array. There's an optional thing to do for performance, which we can prefetch before we try an operation, and that will ensure, or will try to ensure, that the pages that we need to access are located on the device before we access them. Like I said, this is optional, but it does help performance. And then we just launch our GPU kernel as normal, passing in our pointer to unified memory. So those are the three different ways that we're implementing the operations. Okay, so performance, you want to know how they all work, I guess. This evaluation is just on a single platform right now. This is a NVIDIA DGX workstation, so it has 4 Tesla V100 GPUs. It's also got some reasonably powerful Xeon CPUs. And it's got a large host memory, but a somewhat smaller device memory. And I should say we're timing the Arkouda operations. We're calling the Chapel code directly. We're not going through the Python client. So we're not paying the communication cost, which Ben talked about in the earlier presentation. Okay, so the first thing to note is that when we're looking at simple operations like sum, maybe you would expect the CPU wins easily for these kind of operations. This is much faster because merely the cost of transferring data to and from the GPU kills us in this case. So, you can see here the GPU array is an order of magnitude slower than just performing the sum on the device, on the host with Chapel's default sum operation, and even the unified memory operation is not much better. An important thing to realize, though, is that just the kernel operation, so just the GPU kernel, is comparable in speed to the CPU operation. So hopefully that's something that we can use. When we look at more complex operations, for example, a histogram, we start to see some benefit from the GPU. So including the cost of transfer for large enough data, we still come out ahead with the GPU implementations. Now you'll notice that the unified memory implementation is significantly faster than the implementation with GPU array using explicit memory transfer. And probably the main reason for that is that after that prefetch is called, that's an asynchronous operation. The kernel launch can start immediately, and chances are that when the GPU kernel is accessing the data, they're already located on the device. So we don't have to wait for all of the data to be transferred. We're overlapping the transfer of the data with the GPU computation. Just checking the chat. Okay. So we get some advantage from using GPU for more complex operations. If we start to chain operations together, and that's what we'd really like to do in our data science workflow. So we're adding, in this case, we just added a few simple reduction operations to our complex histogram operation. And it's kind of hard to see, maybe if I switch backwards and forwards between these graphs, you can start to see that the GPU is getting further ahead of the CPU in terms of time. So once we've moved the data once, if we're able to chain a number of different operations on those same data, then of course we're going to get more advantage from the higher compute capability of the GPU. So we think that caching data and being sensible about memory movement gives us a way forward for Arkouda workflows. And finally, a quite complicated operation, a sort. This is a really important one, as you've heard, for Arkouda workflows. In this case, we're just doing a radix sort. We're comparing the standard Arkouda radix sort to a sort implemented using the CHIUW library's implementation of radix sort on the GPU, and two different merge algorithms, one for the CPU, one for the GPU. The GPU one is an interesting one based on peer-to-peer swap and merge over NVLink. And you can see that at large data sizes, the GPU merge, which is the green line here, is beating the default sort and Arkouda sort even by a substantial margin. So we're really getting some performance improvement from doing things on the GPU. Okay, so I'll wrap up now and wait for questions. I guess the summary here is that it does look like if we're combining the Chapel GPU API with unified memory, it is possible to support fairly productive and development of high-performance GPU accelerated data analytics operations. You may notice that the algorithmic portability is still a real challenge. For that sort operation, we had to use quite a different algorithm for the GPU as we did for the CPU. In future, we'd like to start working these operations into some real data analytics workflows. We're looking at things like astronomical image and post-processing and analysis. We'd like to port to the AMD GPUs so we can get some figures running on the Frontier system. And of course, we would like to revisit the use of Chapel GPU code generation, which, as you'll hear, I think pretty soon is progressing really rapidly. Okay, I'll wrap up there.
Okay, thank you very much. Let's see, we have one question in the chat. Akihiro, would you like to ask it in person or shall I read it?
Oh, sure, yeah. So can you hear me?
Yes, I can hear you.
Oh, yeah. Yeah, thank you very much for using our GPU Ali. And I'm just curious to know you mentioned the prefetching with UVM, and just wanted to know that if you disable the prefetching, and have you ever compared the UVM without prefetching with GPU Ali? I just wanted to know the impact of the prefetching.
Yes, yeah, the impact of prefetching can be substantial, and yeah, as you might expect, if you don't perform a prefetch, the performance is much more similar between the two methods. The unified memory algorithm is now paying the cost of page faults, at least for the first few accesses. It seems like maybe the page migration engine is actually doing some kind of predictive prefetching anyway, but yeah. To get the best performance, you definitely need to prefetch.
Okay, thank you very much.